And last but not least, in the morning session, we have Brett Morris presenting results from his poster.
So thanks to the judges for allowing me this few minutes to speak. And I'm going to answer some of the questions that were just asked about phase talk in a little bit more detail on one particular planet. And so I want to ask, how does the stellar dynamo change as a function of mass of a star? If you were to have an 80% of the solar mass star with a 29-day rotation period, qualitatively similar to the sun's, how does that change where the spots are on the star, how big the spots are on the star, and the number of spots on the star? So that was the sun, and I want you to recall from phase talk that he found that there seems to be an active latitude at 16 degrees on Kepler 17. On HAPP 11, I'm jumping right to the answers, I'm not going to keep you in suspense. On HAPP 11, we see these three conclusions, and I'm going to show you very briefly how we get to them. We see that the spot latitude distribution is quite similar to the sun's. I'll explain how we get latitudes instead of longitudes. The radii of the spots are similar to the largest sunspots at solar active maximum, and there's way more coverage on the surface of the star covered by spots than on the sun. Here's how we do that. Instead of having a well-aligned planet, like in Kepler 17, we have a highly misaligned planet. It orbits nearly from pole to pole over the star, and that means during each transit, the planet sweeps out bands in one longitude over many latitudes, and that allows us to see where the spots are as a function of latitude, and as you know, that's how you make a butterfly diagram. So this is what our data actually look like. In the Kepler-like curves, there are these really great high signal-to-noise spot occultations in nearly every transit. And we use a forward model to measure the sizes of the spots and their position on the star on all of the transits in 4 years of Kepler data. And looking just at the latitude solutions, we get a nice histogram that looks like this compared to one for the sun over a similar 4-year timescale. And you can see that the active latitudes are centered at 15 degrees, 16 degrees, similar to both the sun and Kepler 17. And if you look at the sun's sequence in mean latitude versus the width of the mean latitude, during the activity cycle, it starts out high on this plot and moves its way towards the bottom. HAPP 11 is within the range of what we observe on the sun. But it has many more spots. This is the covering fraction within the transit chord, which we assume is an essentially unbiased view of the entire surface of the star because we're getting one band in longitude, just one longitude, which then we assume is axisymmetric around the star. And if that's true, then the sun really doesn't get covered by spots very much, but this is covered by about 100 times more spotted area. However, those spots have similar sizes. So we're also solving for the spot sizes from the spot occultations, which are degenerate with position. But the best fit that we get for our spots had a mode similar to the mode in spot radii for the sun at active maximum. It has a long tail out to really large spots that we don't ever observe on the sun, and those are probably unresolved spot groups, multiple spots. But it seems like for the most part we can use our normal flux tube dynamo explanation for how spots work on this star, on this O4 star with a 29-day rotation period. And so the quick results there again, seems to have the same latitude distribution as spots on the sun. It has more spots, but the spots have similar sizes. And so to preempt the first question that you're going to ask is, do we see evidence of a dynamo? Do we see the activity cycle varying during the Kepler years? And the Kepler mission was only 4 years long. So we don't see change in the active latitude on HAPP 11. But we are measuring calcini 2K emission. And so I've been collecting spectra at Apache Point Observatory and combining them with Keck-Hiro spectra to take a look and see how the activity is varying with time. And we haven't quite seen an entire activity cycle yet. We're approaching 10 years of observations, but we're not quite there. So we're waiting to get to that magic number of 11 to actually compare to the sun and see if we have a similar cycle. And I'm going to point out that Monday night I took that data point. So this is as up to date as it can be, but we just don't have the answers yet. So stay posted. There will be a paper on this system on the archive and on the code called STSP, which does the star spot fitting, hopefully within the next month. Thanks.
All right, thank you. Quick question, Andrew.
Hi, do you know why there are fewer spots at negative latitudes positive latitudes?
Yeah, so the apparent asymmetry in the distribution that I show on this slide looks really asymmetric compared to the solar example that I showed. And that's partly a factor of showing that we're looking at a 4-year bin. If you take 4-year bins of solar data, the activity cycle starts in each hemisphere at a slightly different time. And so if you look at any small bin compared to the 11-year cycle, you might find significantly more spots in one hemisphere than the other. And so if you bin up the sun on random 4-year bins, you find that this kind of asymmetry is typical on the sun. It can happen.
Okay. Back here.
Very interesting work. A comment and a question. The comment is that in the sun, we do see active longitudes. So your statement that you're getting an unbiased longitude coverage may not be exactly correct, but that's okay. Why that particular solar cycle? And if you're talking about asymmetries in the northern and southern hemisphere, the current solar cycle may be even more asymmetric in terms of north-south sunspot coverage.
So what's your question? Sorry.
So why that particular 1957 to...
Oh, sure. So this example, bin, I used because the mean latitudes of the sun and the standard deviation in the latitudes is the same as happy 11s. So on this plot where I show the range that you observe on the sun, it's the point that's closest to happy 11. That's why I showed that one. The asymmetry is not as similar. And yes, we know that there are active longitudes on the sun, but on this star, the rotation period of the star is 30 days, and the orbital period of the planet is 5 days. And so every 6 transits, you come back to the same longitude. And our sampling in longitude is so consistent that we're not really able to say anything about how the longitude varies. So within these 6 longitudes, we can say what's going on with the covering fraction.
Okay, I think we're gonna have to break for lunch, but definitely talk to Brett and Faye more and go check out their posters. Thank you so much, Brett. And thank you to all the speakers. We do have a couple announcements before you leave. First is